Berkeley, showing that maybe using the center, the defect center, and to show it can expel magnetic field in a very high pressure situation. Okay, so superconducting science, superconductivity science and technology, as I mentioned, it was, in terms of science, that was discovered in 1911. So it's a very, very old science. It turns out it continues to generate interesting properties. And more people getting involved with this science and then technology involvement here. So I said this superconducting science and technology is forever young. So for young students, if you are interested, get involved and try to make your point in this exciting area. So in terms of science, people looking into the TC and then looking at the mechanism of superconductivity, technology prototypes you can build, including many of the modern things. And then in terms of to explain how do you find them and what are the approaches toward this superconducting science and technology. Basically, there are two approaches. One is theoretical approach, and people call it Einsteinian approach, and the other is empirical approach, that the Edisonian approach. And so the BCS theory, basically, that's Einsteinian approach, and it's based on electron pairing, and therefore, as long as between the electrons there exists an attraction, no matter how small it is, and they'll form pair. And we know electrons are repelling from each other, and from energy point of view, and they are fermion, so they cannot condense into a lowest energy state. So then you try to get it into a boson state. How do you do it? You try to form pair. Once you form pair, it's a boson, so then you can condense into lower energy state, and therefore you can get into the superconducting state in here. There are basically several interesting form for the BCS theory, but the modified form is Macmillan formula, as indicating here. It's the most used formula. I should mention here, there's a mu star here. This lambda is the attractive interaction, electron-phonon interaction. Mu star is a Coulomb repulsion. I mentioned this here because right now, room temperature superconductor, people all thought it's safe, it's already solved. And they all said it's an ordinary electron-phonon superconductor. All you need is just the lambda, electron-phonon. It turns out that the theory predicts the TC correctly. What they did not tell you is the mu stars was an adjusted parameter in this case, here, mu stars. So the mu stars, you cannot accurately calculate it. And so they put in a number and say it's reasonable number, and they get the number. And so even like aromats, and they consider this electron-phonon interaction superconductor, like the hydrogen sulfide, and so on. And then the empirical rules, one of them is Matthias' rule. His rule is very simple. He says you just count how many electrons per atoms in the compound. If you get it to 4.75, you get high TC. If it goes to another 6 point, that's 6.4, you get another high TC. This low temperature superconductor basically can be described by this empirical rule quite nicely. And then, of course, for the high TC, the oxide material, if you use the doping, of copper ions here, using that as a parameter, and Preslin actually came up with this empirical rule, which described high TC pretty well. So empirically, one has this, and theoretically or Einsteinianly, and people use this, can explain it, okay? So in summary, the BCS theory, characteristic temperature, there's a characteristic temperature theta here, and that's the Debye temperature, represent the lattice vibration frequency. And later on, people expanded to even for electronic situation, interaction. And that gives you this so-called isotope effect, you know. So the TC should be proportional to 1 over m minus alpha. This alpha for a simple case should be 0.5 in here. That's the isotope effect. And I mention this because right now when people talk about the room temperature superconductor, they claim it follows this rule. And it's not really rigorously correct, you know, but they just use that number. And then the electron-photon interaction, usually, as you can see here, to get higher TC, you like to get this lambda value as big as possible, But once you get it big enough, and then the lattice becomes unstable, so therefore that's another challenge we're facing, try to overcome. And so therefore, like Ginsburg and co-workers, back in the 60s, 70s, they proposed electron interactions, and which depends on either magnetic fluctuations or the electron-electron correlation. They can bypass this instability issue, and they can bypass the instability issue, get the TC higher and higher, at least according to their theory. So I mentioned earlier, Matthias used the empirical rule, and people call it enlightened empirical rule. Usually when people talk about empirical, that means you don't know what you're doing, just guessing. I think Matthias tried to impress people and call it enlightened empirical rule. So you can see TC basically increases. You plot the TC as a function of an atom per electron, valence electron per atom ratio. It peaks at 2 points. One is at 4.75 and the other is 6.4. So this is the rule. It works very well for the intermetallic compounds, but for the crystalline material. But for the amorphous material, it doesn't follow this rule, but it goes just smoothly, going through here smoothly. But that's all okay. That means this dip is scattered. By scattering, it's removed and becomes smooth, going like this, you know. So this works very well for intermetallic materials, only recognizes the importance of instability also based on this argument. So there was a strong argument in the 70s whether instability will help to raise TC or lower the TC. And there was two schools debating very hard. One is Matthias, and the other is Lou Testati. They went to the same meeting and then argued it out very strongly. It turns out if you sit down and think about it, they are arguing the same thing. So in the before 1986, people based on this BCS approach, and they set a limit on its TC is approximately 30 degrees, the upper limit. And as a result, mostly due to coupled instability, and that leads to many of the instability, like structure instability, charge density wave, and spin density wave, and magnetic ordering, and power instability, and so on and so forth. So from the theory point of view, because the energy scale of TC is so small, so therefore within the uncertainty of the theory, so theory cannot distinguish one from the other. I'm sorry, this thing is not working now. The pointer doesn't work, you know. Oh, coming back. Okay, going like that because of the small energy scale. So then people proposed new mechanisms starting from phonon, electron, magnetic or charge, and so on, and including a different kind of mechanism have been proposed. So before 1986, experimentally, TC is 23.2 degrees discovered by Lou Testati in 1973. And then so people started looking for novel materials. And theoretically, they feel that's the limit, which was restricted by the instability of the material. So at the time, during that period of time, people working in superconductivity are facing the confidence crisis. people thought that was the end of the days of superconductivity research. It turns